and this is a negative slope field. Sorry. This is T2. Does this make sense to everybody? Yes, question.
Yeah, so the slope of T2 is greater than the slope of from T1, right?
Yes.
But those are negative slopes, right? So
Yes.
wouldn't a more shallow slope be?
No, the magnitude.
Okay, magnitude.
Magnitude, right. Because you see, it was, let's see if I think I erased it, but here is the idea. Minus K1 dt1 by dr is minus K2 dt2 by dr, the negative sign vanishes.
Okay.
So I'm looking only at the magnitude of this one. Alright, any other questions on this problem, please? Yes?
How would you draw the heat flux?
You can draw the heat flux. Well, it's not going to be constant for either of them. That's one thing. Right? Because you're going to see that there is heat generation taking place there. So heat flux would be linear for this situation. And it is going to be a 1 by r situation for this one. Okay? I'm not going to do it because you have a problem in your homework where I've asked you to draw the heat flux. But I'll post it in my solutions. So if you want to calculate the heat flux, Q is minus K1 dt1 by dr, so this is going to be linear, okay, positive, because dt1 by dr is negative, so this becomes positive, linear and positive. And then if you look at the second one, this is at material K1, at material K2 is minus K2 dt2 by dr, so that's going to be minus K2 C3 by r. So this is a 1 by r dependence, so non-linear here, but negative. Alright. Any other questions on this problem, please? This is all I have planned for the day, and I think we have like a few more minutes left. What I want to do next, we are going to shift gears and we're going to go back to the situation where the energy generation is going to be switched off again, and we're going to start looking at thermal resistance networks. Okay, so which is a very useful idea to know, and when we do that for radial systems is where we will look at the idea of the critical thickness of insulation and so on. So on Friday we will have class on Zoom. Okay, I just mentioned it at the beginning of lecture. I'll start off by drawing an analogy between electrical resistance and thermal resistance. In electrical resistance, the driving potential is the voltage difference. In thermal resistance, what should be the driving potential? Temperature difference. In electrical resistance networks, what is the flow variable? It is the electric current, which is the rate of change of the quantity of charge that is stored. dq by dt is I. What is the flow variable in thermal resistance networks? What flows in electricity is current. What flows in thermal systems is heat. So the rate of heat transfer is going to be our flow variable here. And this is possible only when the heat generation is zero, because you want to have a constant flux, and only then can I talk about the idea of a thermal resistance. Otherwise we can't talk about this. If I have heat generation, the idea of thermal resistance is nonsense. Okay? And we will go to radiation in some time. We still have some time for that. You will see a different type of a thermal network that is drawn there, which is different from what we do for conduction and convection heat transfer. And at the end of the day, towards the end of the semester, we will combine all these elements together to have a total resistance network. Okay? Thank you.